to do well, so let's just refocus and get ready for today's lesson, which is actually very easy, and you should have no problem getting your homework done in class, okay? So we should all be on page 26, ready to get started. Kaylee, would you mind putting your bag down? Thank you. Thank you so much. Okay, so yesterday we had the work day, work on the quiz. Don't forget the quiz closes Friday. Guys, I say midnight because that's the closest time, but it's really 11:45. So that kind of bit me in the you-know-what before. It's 11:45 is the latest time I'm able to put it to, because midnight's actually technically the next day, and that just confused people when I would do it like that. So 11:45 is when anything closes in AP Classroom, but I accidentally will just say midnight just to round it to that, but some people really needed that 15 minutes, so just know that. Okay. And so on Friday we did geometric sequences, which were, a pattern of numbers that you multiplied to get the y values, and we learned how exponential functions had the same characteristics of that, except for the domain was a little bit different. So we're just going to go a little deeper into exponential functions today and tomorrow. Really simple, nothing at all for you to be stressed about. We saw an exponential function on Friday, but we wrote it in f of n instead of f of x, and the x was an n, no big deal, same thing. We learned that a is always a sub 0. It's always x, when x is 0, what is y? Which means it is the y-intercept, right? That's always going to be the y-intercept. And in a word problem, it's your initial amount before time starts, 0, before the ball dropped, all the different things we talked about. So that's the importance of the a value. And there's only one other number, and that's the b value, okay? The b value, if it's greater than 1 or between 0 and 1, meaning it's not ever going to be negative, okay? That's going to be exponential growth or decay. And sometimes you'll hear it called a growth or decay factor, and that's what you're multiplying by with your y values, okay? Whether you're multiplying by 2 or 3 or 1/2, okay? And one other thing we need to know about exponential functions, I'll just squeeze it in here, is that exponential functions, I'm going to do a lot of abbreviating here, so if you don't want to abbreviate, you can write it out. Exponential functions have a horizontal asymptote that dictates end behavior. And we've heard that statement before. When we talked about rational functions, they were like the curvy graphs, the branches. You'd have like two in opposite quadrants. We had horizontal and vertical asymptotes. We had holes, if you remember all that stuff. And horizontal asymptotes would dictate our end behavior. You'll see that in a second. And as far as graphing, I've told you guys this many, many times in this class, that we're not really into graphing. Like, we're into it, but we're not into it. We're not into, like, making perfect graphs and XY charts and plotting points perfectly. We sketch graphs here and there. What we really focus on in this class is all the characteristics of graphs, all the things that we can say about the graphs and all the parts of it and stuff like this. So here we have an exponential function, and we're going to do one simple XY chart and actually plot it, but after this you'll see in a few minutes how easy it is to graph these. Now, if you look at this equation, this exponential function, it's only got one number in it, right? And we just talked about how there's an a and a b. So the number that has an exponent is the b, okay? So 2 is our b value. A, if you don't see one, anybody want to guess, or educated guess, whatever, what the a value would be? It's 1. What do you think a common mistake would be? 0. Yeah, a will never be 0, okay? So it's just like when you have a variable and you don't know what number is in front of it. If you don't see a number, it's a 1. And when you don't see the a, it's a 1, right? And so what we're doing here is we're plugging in these x values and simplifying them. And what I do like about this example, even though we don't really want to have to do too much perfect graphs, is the opportunity for us to talk about negative exponents. Sometimes I see students think that negative exponents mean the base is negative, so that this would equal -4, and it doesn't. A negative exponent actually means you cross the fraction bar to change the sign of the exponent. So this is clearly in the numerator. So if you cross the fraction bar into the denominator, it just changes the sign of the exponent. Remember we talked about there's a 1 in front, so that's just 1/4. Calculator could do that work for you as well, but really the easiest way whenever you have a negative exponent is just to think what would it be if it were positive. 2 squared is 4, but since it's negative, we'll put the 4 in the denominator. Okay? 2 to the first power is 1, but since it's negative, we'll put it in the denominator. Anything to the 0 power is 1, and then you can see we're just multiplying by 2 as we go through there. Okay? All right, so let's just plot the points. Negative 2 1/4. That's a teeny tiny number. Just estimate it the best you can. And then negative 1 a little bit higher. 0, 1. There's that y-intercept. And then keep on going. And you can see it makes like that J shape. I did tell you there's a horizontal asymptote on this graph. On every single graph we do today, it's going to be right here at y = 0. Okay? And when we learned about horizontal asymptotes before, vertical ones as well, we learned that you can kind of identify where an asymptote is. These numbers that are getting really small as they get near 0 are telling you that they're approaching an asymptote. It's like they slam on the brakes and they get kind of jumbled up close together because they're trying not to get to the 0. Okay, so you would not want to include that in your graph. You would connect it with a smooth curve, arrows on both ends. It keeps on going, right? So the graphs look kind of like a J, and in a minute when we have decay, number less than 1, it'll go the other way, and you'll see both of those in a second. The domain of these guys are all real numbers. Every x value, you can use any x value. Look at your arrows, they go left and right forever. Nothing is stopping them from going left and right. We are being stopped from going all up and down, right? This asymptote is keeping all of our points above it, so that's from 0 to infinity. We know we always use parentheses on infinity symbols. How about the 0? Is that going to be a bracket or a parentheses? What say you? Parentheses, because it's not included. Remember, the whole point of an asymptote is it's not part of the graph. It is not part of the graph. And so we cannot include it. Everything above it is included, but not the 0. Okay, so don't forget that. Here's your end behavior statements. As x approaches positive infinity, so that's going to the right, y is approaching positive infinity as well, right? We're going up. And as x approaches negative infinity, that's to the left, what is our y value approaching? Geo, come on, Geo. Gotta wake up. It's approaching 0. Yep. Good job, whoever said that. Thank you. Asymptote, we just talked about it. It's always going to be y = 0 today. Intercept, yep, we got one, 0, 1. Concave up or concave down? Of course. And there's 2 more questions they're going to ask in the homework, so I'm just going to add them here. Do we have any extrema? So let's remind ourselves what extrema are. Those are your mins and maxes. Remember we had global and local and all that stuff? The whole point of asking this question is no, there are none, because exponential functions are always increasing. Like this graph will be an increasing function forever. It just keeps going up. It's never going to turn around. It's always increasing. Or if it was a decay, if the b was less than 1, it would always be decreasing. So there's no turnaround. There's no place for you to have a min or a max. So you will never have extrema on an exponential function. And continuity. It's going to ask, does the graph have continuity? Yeah. And that simply goes back to on Friday when we graphed it was graphed for us, the geometric sequence. It was just the points. And remember, I said it's not a typo that they're not connected, because in a sequence, we just want the first term and then the second term, not everything in between. That's called a discrete graph and does not have continuity. This one does. Yes, this is a continuous graph, meaning it's connected. All the points are connected. It's continuous. Okay? So just being able to name a whole bunch of stuff about the graph. And it's kind of the same answer every time, I'm not going to lie. All right. Next page. So what this is asking for is for each of these functions, state the initial value, the base, and say yes or no, it's an exponential function. We're not going to bother with the y. Here's the y of it. It should be in this form, right? A and b are numbers, and this should be an exponent that is a variable, right? That has to be a variable. It's not going to be a 3 or a 2 or a 1/2. It should be x or n or something like that. So right away, initial value here, remember if there's no a value, it's 1. Base is 2. Of course, this is exponential. It's the one we just graphed a second ago. Okay? It's in that form. Second one, initial value 4, up, problem already. That should be a number, and then look at your exponent. It's a number. It should be a variable. If the x and the -3, or if it was a positive 3, were switched, then it would be. But no, it's not in that form. Okay? Just because you have an exponent doesn't mean you're an exponential function, is the point. This one has a 5 and an e, but it has an x and a -1. But no. So this one I'm going to tell you is exponential. Here's why. E is a variable, right? So I just told you guys on the last one, this variable made it, is one of the two reasons why in example B we said no, because that should be a number. So when you look at the E, you should be like, wait a second, you said a letter can't, that has to be a number. So just like pi, you guys know what pi is. Pi is this number, right? Pi is actually a variable. It's a Greek letter. And so it's a letter that represents a very, 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 very important number, okay? So we don't use pi for like, when I'm like, pick whatever variable you want for this problem, we would never use pi. Same goes for E. E is a very important number in math problems. Compounding continues, like the PERT problems. Natural logs have bases of E. We'll talk about E more later. But it's such an important number that it got its own letter that stands for that number, okay? So these are variables technically, but they're known variables, not like unknown. We don't know what X represents. We know what pi and E are. So this one is a exponential function, okay? How about this one? We got a number here, we got a number here, and we have an E as our exponent. Would that make it a yes or a no? No. It should be an unknown variable, okay? So the fact that they used the E is reserved for this one purpose. So we would never use E or pi, but that's a Greek letter anyway. I don't think anybody would choose that. Out of the 26 letters of the alphabet, we would never use E as our choice, okay? Okay, you have some problems in the homework where you have to plug in for X and simplify. I don't need to do that for you. If you plug a 2 in there, 2 plus 1 is 3, 3 to the third power times 6, fine. You guys got that. But I do want to talk about this one. If I'm going to plug in a fraction exponent, that is telling you something. Anytime you have an exponent that is a fraction, what that means is you are going to do a radical around that number. So if I take the 8 and put a radical around it. Now, by the way, this symbol is a radical. It's a very generic term. If I don't do anything to it, it's a square root, right? This would be a 2 right here. We just don't write it. But the fact that it's a 1 and a 3 means this, okay? The numerator of that exponent's fraction goes on the base, so it's 8 to the power of 1, and then the 3 is the root. Okay, this is going to be really big in the next coming days. We're going to see this a lot, so I really want you to understand it. Cube root of 8 is 2. A really common one is the fraction 1/2, because that's the square root. You're going to see it all the time. Like all day tomorrow in our lesson, you're going to see numbers to the power of 1/2. Just know that means the square root of it. Do you have to write that? No, you can know. Oh, anything to the power of 1/2 means the square root of that number. If you have trouble, and this used to be a big concept in Algebra 2. I don't know if it is recently. I haven't taught Algebra 2 for a few years, so I don't really remember. But I remember when I used to teach this a lot, where they had to do this a lot, I would have students forget where, like, who goes where. Where does the 1 go? Where does the 3 go? And they'd get them confused. So I came up with a little dance for you. if it helps you. But if you make a fraction out of your hands and do right over left, so if this is 1/3, and then you hug somebody, like think about it, you wouldn't hug somebody like this. So right over left, hug somebody, so 1/3. So the 1 goes in here and the 3 goes here. I would have people during the test look like they were dancing. They'd be going like this to kind of remember it. I don't know if it helps you, or maybe you're like, I don't need a trick, I had it already. Whatever. Okay, so we know 8 to the 1/3 power is 2, and so when we plug in 1/3, we get negative 10. Okay? Good? Almost there. This one and the last page are really what I want you to get out of this lesson. Can you be given some information and write a exponential function with it? We're going to call it g of x, and it says the value of g at x equals 0 is 3. Okay, that's code for my y-intercept, right? When x is 0, y is 3. I even filled that in for us. And the output value of g doubles at every 1 unit increase. So as we go up by 1, these are going to double. That makes our b value 2. Really hard, right? It's really hard. And now double them. And you could complete the chart if you need to. You could graph it if you needed to. We don't need to. Good? Last little bit, most important stuff. Being able to look at a table of values. This is one of your FRQs on the AP exam. You're going to be given a table of values, and you have to say what's going on in that table. You have to say, is it linear? Is it quadratic? Is it cubic? Is it exponential? We're in exponential, so I'm hoping you guys can look at this and say, okay, I'm going to skip over the fractions, but I can see that I'm multiplying by 2. Okay, the minute I'm multiplying by a factor of 2, we'll use that word, that means it's exponential. Okay, so if I have to write an equation that represents this, I need A and I need B. So again, if your y values are multiplying by the same number left to right, that means your graph is exponential. B value is what you're multiplying by. A value is your y-intercept. Done. Right? If we were adding 2, that would be linear. I think one of your homework problems actually slips a linear in there. But if you're adding the same number, that makes it linear. This would be your y-intercept also, right? B value. And then the slope is whatever you're adding. And this one, it looks like we have, so this one was growth, right? Because b is greater than 1. This one, the y values are getting smaller. By what? I don't know, maybe. So don't forget, you can easily test it by taking any two consecutive numbers, 5 over 10, 10 over 20, and simplify it, and that will give you your b value. That means we're multiplying by 1/2, or dividing by 2. And there's your a value. A is 5, b is 1/2. So that's decay. And let's just, this is the type of graphing you need to be able to do. In fact, it would just be multiple choice anyway. But sketching this graph, you do not need to get out a graphing calculator or make an XY chart. Simply look at two things. Y-intercept is 3, right? My y-intercept is 3. And 2 means there's growth happening. So I should have an increasing function. It should look like a J. So it would look something like this. That's as good as it has to be. Let's remember that we have that asymptote at y equals 0, so we won't graph on that. And because our base was greater than 1, it's a growth factor. The graph is increasing. Limit statements already started for us to fill in. Be careful. Remember, the order that they're written in doesn't matter. I tend to put negative infinity first. Look, they're putting infinity first, so just always read it carefully. This is your right, this is your left. So as x goes towards positive infinity, the y's also go to positive infinity. And where are the y's going to the left? Towards what? 0. Domain, all of them. and range 0 to 3. Right? Easy, easy. One more. Y-intercept. 1, 2, 3, 4, 5. That looks good. Decay, so it goes the other way. So your graph should be decreasing. So starting up and falling as we go left to right. Don't forget we have that asymptote at y equals 0. Because we're decreasing and b was less than 1, that would be called a decay factor. As we go to the right, our y values approach 0 to the left, infinity. Domain, this is really hard. This one's hard right here, guys. Told you it was hard. This is really hard. 0. Just kidding. Try to make sure you're paying attention. Okay? That's it. You done good. Now keep doing good. Remember, guys, if there's anything I can help you with, explain better, calculator stuff, yesterday's, Friday's work, whatever, always ask. I want to help. I like to help. I get paid the big bucks to help. I can look. Yeah, just give me a minute and I will. Yeah. Yeah, I don't let you guys see your scores till it closes because. Yeah, but I can look at it. All right. Get this on canvas today.